Okay.
I'm not wrong.
According to René Descartes, the human body is a mechanical system designed by the hands of God. Borelli, a student of Galileo, considered the human body as a system of levers. Okay? So here it is. Levers. Can you fill that in for me? I knew you could. So let's explore that. In our body, the bones act as a rigid bar, and the joints the fulcrum. That's the point where it pivots. It is through these so-called human levers that we are able to move. No matter how slight our movements, it is to talk, to walk, and even eat, all lever motion. This is all review of your elementary science class, since levers have been taken out of secondary school and moved down to elementary. So you will see the different orders of levers. The first order is a teeter-totter.
Who says teeter?
Seesaw.
It's a seesaw.
A seesaw.
Okay. The second order is a wheelbarrow, where you have a massive weight in the middle and you'd lift it up at the end. Why is that? Because your effort is going to be a lot less. So, and the third order, with no mechanical advantage, but it gives you a larger range of motion. Okay, enough seeing those little animations? Equilibrium. It is the condition of where forces are applied but simply cancelled out. These forces may even be large enough to cause permanent deformation. Time to fill in your sheet. Equilibrium is the condition of forces where forces are applied but cancelled out. So it's kind of like F net equals 0. Surprise! Statics. Statics is concerned with the calculation of the forces acting on and within structures that are in equilibrium. Filling it in. It is concerned with the calculation of forces on objects that are in equilibrium. So this chapter 1.3 from the workbook is called Static Equilibrium. That's what we're introducing now. It is forces acting on structures in it that are in equilibrium. Okay? So there are two types of systems we're going to divide them up into. There's concurrent and non-concurrent. Concurrent systems occur when all the lines of actions of the forces act on the body at a common point, an intersection point, like the knot from the rope problem that we did yesterday. That's called concurrent, all acting at one point. Non-concurrent systems are when the forces are acting at different points upon that object. So here's the notes. I help you fill them in. I know it's sad that I help you this way, but then everyone gets the same notes. All forces acting at a point like a rope and a knot. Non-concurrent.
Oh, whatever.
Coming right up. Non-concurrent systems, when forces are acting at different points. Here's another one. Observe. There is the strut. It's labeling it. It's like a 20-meter long strut. There's a mass hanging from the top of it. There's a hinge at the bottom, and there's a restraining cable. Observe the forces that are acting on this. Red strut. there is a force of gravity pulling down on it there, which will be 150 times 9.8. Whoops. There is the force pulling down on it in the middle. This is its own mass. The mass of the strut itself has a force acting on it, the center of gravity. We'll learn about that. There is this rope pulling along it in green there, and it's a restraining cable. There's also one more force acting on this red bar, and it's the force of the hinge at the bottom that's pushing up on the red bar. So in this case, there are four arrows acting, four forces acting, and they're not all acting on the same part of that red bar. This is because it is non-concurrent. Many forces acting upon an object at different points. Non-concurrent. Particle and rigid bodies. Okay? The distinction has to be made whether the object is being acted upon by a system of forces is a particle or a rigid body. A particle can be considered as a point of mass, all forces acting on it. That's physics 11. Every system that we've done in physics 11, all the forces acted at the center of the object. A car accelerates and there was a force of gravity and there's a force of friction. We didn't consider the length of the car and how far away from the center of gravity the tires were and the friction. We just said all these forces are acting on the car. A rigid body is when the object actually has some size to it in space and does not change its shape or size. Distinction has to be made whether the object being acted upon by a system of forces is a particle or a rigid body. Here are the free body diagrams of a particle system, aka physics 11, and a rigid body system, just chapter 1.3. Physics 12, the rest of physics 12 is the particle. Chapter 1.3, static equilibrium. The objects now have size in their free body diagram. So we actually draw a free body diagram like so on the right hand side. Also, therefore, a particle system is concurrent. And a rigid body system is non-concurrent. A rigid body is non-concurrent. Usually. It could be. We could have all the forces acting on the rigid body in the center, but yeah, that's boring. That's physics 11. And that left free body diagram, that's a free body diagram of a 747, a ski, it could be a house, it could be a car. It's the same free body diagram for everything. But the rigid body one, that's a rigid body of up at an angle there. Okay, we need a timeout.
Go back for a second. I didn't quite get the last part. I didn't quite get the last part.
Rigid is non-concurrent,
Yeah.
and concurrent is a particle. We already have the definitions of concurrent and non-concurrent on slides before.
How would you know? All
Don't question it.
that. It's Disney, don't question it.
Don't. It's cool.
2 and 2. Or just go try if it's like right there.
No.
Where'd it go? It should be on this. He has Newton rules somewhere. Try that. Yeah, but it would be just gravity.
That was enough time to digest. Now here we go. Translational equilibrium. Translational equilibrium. Equilibrium is a condition where there is no change in the state of motion of the object or body. An object in equilibrium may be at rest. It can also be in motion, provided that its motion is at a constant speed and in the same direction. Translational equilibrium is a condition where there is no change in the state of motion of the object. A equals 0. Is a condition where there is no change in the state of motion of the object. An object that has no net force acting on it is said to be in translational equilibrium. This condition of translational equilibrium is usually referred to as the first condition for static equilibrium and may be expressed in the form of the sum of the forces equals 0. So the first condition of static equilibrium, also known as translational equilibrium, is expressed mathematically as the sum of the forces is equal to 0. The sum of all forces in all directions are equal to 0. No net force.
Sure.
So, in equation format, I kind of like this one. Sum of the forces in the x equals 0. Sum of the forces in the y equals 0. It's very physics 12-y because we're in 2 dimensions in physics 12. We look at the x direction, then we look at the y direction. It's very physics 12-y. Doesn't that look nice? Okay. Here's a typical question. We're not solving it. We're just looking at how the first condition is used in this one. Just pay attention. So the sum of the forces in the x equals 0 and the sum of the forces in the y equals 0. There's only forces up and down here. There's none left and right. So what's the first force? Well, there's our beam that we're looking at. The red thing I just made red. There you go. There's a force of gravity from the center of gravity. COG, center of gravity. The object itself. It's in the center. There's the weight of the diver. The force of gravity of the diver pushing down on the board. And in the question above, it says support A is providing a 3,000 Newton force directed downwards on the board. So there's a 3,000 Newton force, a force A, on the left-hand side there. There's one more force there. it's B, and B is pushing up on the board. And we'll label it. Now I'm going to hide everything. There's our free body diagram. We have forces up, forces down, and we have that the sum of the forces have to equal 0. Well, if the forces equal 0, then the forces up is equal to the forces down. The forces up is FB, and the forces down is FA, F center of gravity, plus the force of gravity of the diver. We know those three to the right. We'll now be able to figure out that force B can be calculatable. We can calculate it. See, that's how we apply it. It's pretty cool. So was this. But now we look at, we see the red arrows there, but that's not good enough for us to solve in Physics 12. This was elementary school, first order, second order, and third order of levers. To solve it in Physics 12, we also have to have the force that's not mentioned there. The force of the fulcrum pushing up. Each of these is missing a force upward at the fulcrum. Each one is represented. The first order, the fulcrum is the neck pushing up on the head. The second order, it's the toe, the ground pushing up on the toe. And the third order, it's the humerus pulling up on the radius and ulna at the bottom. Big words, yes. Just to think about it. That's all I'm getting you to think about. We're not solving these things, but you can see that, man, this is very applied. We can get there. So the recap. The first condition for static equilibrium is the sum of the forces equals 0. Mr. Curl kind of likes writing down sum, that's the sigma, the sum of the forces in the x equals 0, and the sum of the forces in the y equals 0. Torque. It's a Greek letter tau. I believe it's a lowercase tau. It's a Greek letter. As I said, there's too many letters and I tried to avoid them so that you don't get confused. But this one we can't avoid it. We're going to use tau. Tau is a vector that measures the tendency of a force to rotate an object about some axis. The magnitude of a torque is defined as the force times its lever arm. Lever arm is just another for distance. It's a distance. The lever arm is a distance. Just as a force is a push or a pull, a torque can be thought of as a twist. So it was given there in words that torque is the force times its lever arm. There's our first look at the formula. Torque is equal to force times the lever arm distance. Now, it is a vector. And these are vectors. And it actually isn't a dot product, it's a cross product. It has a little X there. Okay, we'll talk about that another day. So, torque, tau, is equal to force times distance times the sine of the angle between these two vectors. So this is the point of rotation. And there's a beam here. You don't see it. There's the beam. And it could be longer. but there's a force pushing on it at this point. So that distance is r, and that's the r vector. And the force is applied to it there, and the angle between the force and the lever arm is theta. So the formula for it is torque is equal to force times distance times the sine of theta. Have you seen torque somewhere else?
Car tire.
Cars.
Torque the wheel.
Okay, well, here it is. Here's what a definition of torque is, number 9. A twisting force that tends to cause rotation. Here's another word for it that you might pick up, or words from it. Torque, moment, or moment of force is the rotational equivalent of a linear force. Rotational equivalent. It is not a linear force. The concept originated with the studies of Archimedes on the uses of levers. Just as a linear force is a push or a pull, a torque can be thought of as a twist or a tendency to cause rotation. Torque. Okay? Here is a tool called a torque wrench. It's meant to measure basically how much rotational force you are applying on a nut or a bolt, to how tight it will become. You want the nuts on your tires of your car to be a certain tightness. You don't want them coming off, but you don't want them too tight that they don't come off. So they use torque wrenches. They can. And the unit for torque is a Newton meter. Newton meter. And at university, you learn that torque is actually a vector, and it's in a third dimension, and then you have to use the right-hand rule to determine the direction of it. We're not going to be dealing with it as a vector. Right now in Physics 12, we keep it as a scalar. Another term that I've already used right now, a center of gravity, a COG, a cog. The center of gravity, or the center of mass, is a useful concept when dealing with equilibrium problems. Each of the particles making up the body has its own little piece of mass, a little own weight, and the mass or weight of all the little pieces of an object becomes its actual weight. And this center of gravity of the body is the point where the entire weight may be assumed to be concentrated. And in Physics 12, the center of gravity in an object is where its entire weight, Fg, will be assumed to be. And in a uniform created object, the mass is in the center of the object. Got it? Last concept. Slide number 39 or something like that. Rotational equilibrium. A necessary condition for a body to be in rotational equilibrium, that is, not spinning and not spinning faster and not spinning slower, but at rest, is that the sum of the torques must be 0. And this is known as the second condition for static equilibrium. The second condition for static equilibrium, rotational equilibrium, is sum of the torques equals 0. sum of the torques equals 0. The next step right underneath it is sum of the torques clockwise is equal to sum of the torques counterclockwise. Okay, you guys with your digital clocks don't know what clockwise is and counterclockwise? You do?
You haven't hit that generation.
I haven't hit
Once
that
you hit the
generation?
grade 8s or 9s,
That's the nines,
when
that's the
you're
grade
getting in
nines.
there.
Okay.
I don't get that anymore.
My brother got
That's
it.
And the red clock up there,
No way.
it's not set for the right time, but that's a counterclockwise clock. The motor runs backwards, but the numbers are also backwards, so it tells time backwards, which is actually working. Anyway. So, there are two conditions for static equilibrium. You have your two conditions for static equilibrium? You've written them down? So one more quick learn on torque. One more quick learn on torque. We have the axis. We have the object itself. And we have the force being applied at point A. So we draw the position of the vector between A and Q, where the force is being applied. We draw the straight line along it. And then we have to make the angle. Now, which angle do we choose? Theta or beta? Which angle do we choose? Do we choose theta or beta? This is an intersection of two vectors, and it doesn't matter. Why? Because the sine of supplementary angles are equal. So if I say this is 70 degrees, and this angle over here will be, 110? And you ask me, which angle do I choose? It doesn't matter. So it can be the sine of beta, or it can be the sine of theta. And here's our recap of static equilibrium. Static equilibrium is the combination of translational equilibrium and rotational equilibrium. This physics state is summarized by the following formulas. Sum of the forces in the x equals 0, sum of the forces in the y equals 0, and sum of the torques equals 0. That's it. Now, you guys all need to know what the next step is. But this is the rule. That's it. That's it. That's all I wanted you to be able to get down. But under each of these, this will be the forces left equals the forces right. This is the forces up equals the forces down. And that means the torque counterclockwise is equal to the torque clockwise. So each of those I've given is the next step in any static equilibrium question. So in Physics 12, when it says, or you figure out that this is a static equilibrium question, all of those things I wrote there are what you write down. Now, which one do you start with? I don't know. It depends on the question. But these are the first two steps of rotational equilibrium, first two steps of translational equilibrium that make up static equilibrium.
That's like a classic.